DeepSeek R1 is a large language model that was recently released by the Chinese startup DeepSeek, which has been making waves for apparently matching the reasoning performance of OpenAI's best closed models from merely a few months ago, while providing weights and a lot of information on the training process freely. Along with the full, approximately 670 billion parameter model, they also released several small so-called distillations of the model, which are basically smaller models that have been fine-tuned on transcripts generated by the full-size one, in the hope that they will absorb some of its reasoning capabilities in the process. Several of these can be easily run on consumer hardware, such as this gaming laptop that I'm currently using. Let's take a deeper look at the reasoning process of one of them, namely the one based on the 7 billion parameter version of Alibaba's Qwen2.5. I will be using Autopen, an open source program that I have been developing for this purpose. An LLM is essentially a function that produces, given any piece of text, a probability distribution over words and word fragments that may immediately follow it. You can see the probability of each word given what comes before it, as a sort of measure of how surprising the model finds this word. Roughly speaking, although this is a simplification, LLMs write by picking the least surprising word and attaching it to the string of text that they're operating on over and over again. Autopen lets us visualize these probabilities, seen here by more surprising tokens being shown with a darker shade of blue in the background. Jump back and forth between the different choices that could be made, and explore how the model would proceed after any given choice. Let's look at a concrete example. Suppose we start typing the quick brown fox. And then we can see that the most likely word to follow after this is jumps, followed by over the lazy dog, period. As we advanced along the sentence, we could see different sentence pieces appear below it in gray. These represent the next highest probability tokens, that is, word fragments, to follow after the word under the cursor according to the model, followed by the most likely tokens that the model would choose after those. We can try choosing a different word to follow jumps. After over, the next option, as we can see, is across, followed again by the lazy dog. The status bar down here shows the specific numbers associated with each choice. These represent the logarithmic odds that LLMs customarily operate on. If we instead choose A to follow after across, the most likely completion becomes a river. Going back and choosing V after all, we see that instead of a lazy dog, the next likeliest option here is once again a river, followed by a fence. As we advance further down, we start encountering various gibberish and also more unrealistic options. Note that whatever we choose, its evident preference is to segue into more lecturing about LLMs due to the text that we have in the buffer before our example sentence. But without further ado, let's have a look at how the model fares in a simple mathematical problem of the kind it was actually trained on. So here is an example problem. Josh is an obsessive soda drinker. His favorite soda costs $1 per can to buy. If he returns an empty can, he can get 20 cents of deposit back. Josh has run out of money, but after cleaning his room, he has found 141 empty cans. How many more cans of soda will he be able to drink? In DeepSeek's training, the thinking process is initiated by a special tag which is written as follows. So let's put down the tag in our buffer. As we can see down here, it has been passed as a single token. And then just see what happens if we let the model do its thing. Very chatty style, but it's not sounding. So I guess you can really see that the model is basically trying to talk to itself somehow. Simulate a realistic internal monologue. And at some point it starts to make the argumentation more formal. Yeah, let me complete that. Yeah, that's correct. Use that money to buy more soda cans, right? Yes. $0.20 left over, which is 20 cents. And you can do something with that. Well, yeah, you should be able to. Yeah, there are a lot of these paragraphs that start with wait, where it is basically trying to do a line of reasoning that it has already tried all over again. If $1 can buy one can, then to get $0 back. Note how it's already lost track of the money that it had saved earlier that it couldn't directly use for cans. I'm suspecting that this will probably give a wrong result at this rate. And I'll switch to doing a more kind of step-by-step representation of the reasoning. Right. This one can do 20 cents, and he can't buy anything with 20 cents because he needs a full $1. So adding up the cans, he can buy 28 plus 5 plus 1 equals 34 cans, which is not the right answer. So as I already expected earlier, it has kind of lost track of all the cent amounts that it couldn't use at a given step. So here it lost 20, here it lost 60, and here it lost 20 cents. So if it had actually kept track of all of those and combined them, it should have been able to buy another can. But it did not realize that. So now let's see if there is something about this line of reasoning that we could fix, or some slightly lower probability course that it could have followed where it would have figured out what it was supposed to do. Yeah, so somehow like you can maybe see that at this point it's no longer talking about the 20 cents that it had from earlier. So what if we looked for an alternative where it still is aware of having those 20 extra cents? And return those 28 cans to get 28 and 0.20 equals $5.60 back. Now he has, what are the alternatives here? So now he has $560 plus any leftover from the previous step. As he's saying, wait, hold on. Is this going to be good enough? Let's have a look. Wait, hold on. Let me break it down step by step. Cans. Now the key display is a little bit in the way. But 141 times 0.20 equals 28.20. 28 to buy 28 can, even with 20 cents. Now he has 28 cans, and he returns those, he gets 560. So now he has, yeah, well, this is looking better already. Totaling 580. And then let's see where this goes if I just let it continue. 580. Yeah. To 0.80, he has $1 left. So with the $1, he can buy one more can, leaving him with 0.0. Now he has one can, returning what gives him 0.20, and he can't buy another can with just 20 cents, so he stops here. Wait, this seems a bit complicated. No, does it now? Yeah, way to trip just before the finish line. Let's see if there was some alternative choice up here where it actually would just start tallying up the results of that step-by-step reasoning. So if we start to, let me tally up how many cans he bought in total. Starting from step 3, he bought 28, then 5, then 1, then 1. So that's 28 plus 5 plus 1 plus 1 equals 35 cans. Nice. So in the end, we needed to intervene in 2 places to stop the model from going off track. Let's just check out what were the differences in logits there. So down here, we have a difference of about 3 between the top choice and the that we chose. Since we are natural log units, that's probably a factor of about 20. So it would have been maybe about 5% likely to pick this over the top choice that it wound up picking this way. This seems a bit complicated. And at the first branching point up here, if we look at this V, the difference is about 2. So that would have maybe been 10% likely relative to the top choice that got the wrong result. So one thing that's also worth trying out is if we just go back to this initial branch that we picked here, what would have happened if we instead had just explicitly injected a thought to remind it of the leftover money that was not taken into account? So if, for example, we went here, and then we inserted some text saying that wait, but he also has the 20 cents left over from earlier. And then we delete all of this and see where it will go instead of it. So 560 plus 020 is $580. So we can buy 5 more cans, right? Well, that's no good. Looks like it totally forgot about reusing the leftover coins up here. So let's just do this a blunt way and try to inject this step explicitly. And the leftover 0.80. I'm a bit so confused now. Well, there we go. It did it in the end, although we did have to help out a little. So all in all, I think these are some pretty impressive results for a 7 billion parameter model that is only about 5 gigabytes on disk. It is really eerily like listening to one's own thought process, well, maybe while one is a little drunk in solving a problem like this. So I've also seen in other experiments, it seems to have learned to follow this pattern, where it first restates the problem to itself, then tries to talk through it informally, while also constantly second-guessing itself with those wait maybe paragraphs that you see here. And then finally tries to somehow break it down or structure it step by step and extract the final result from that, whereupon it once again proceeds to second-guess itself. It does have a certain tendency to get stuck in loops and dismiss correct thoughts as too complicated and the like. I do wonder if you just were to let it keep going, it would eventually stop and terminate the thinking process by itself. Another interesting exercise one can do is changing up the numbers after the thinking process is done, and seeing how the now invalidated intermediate results turn from expected to surprising. So if we, for example, change this to a 2, you can see it reevaluate the whole string. And if you follow the highlight, here you see that now this 4 is not the number that occurred in the problem setting. So now you could go here and maybe also update that one. And then you'll see that now it will be upset about the next instance of 141. And if you keep doing this while leaving the intermediate reasoning alone, you could even imagine using the LLM reasoning as some sort of natural language spreadsheet. And I think I shall leave it at that part. The source code and some binary builds for Autopen can be found at the GitHub link, which I will post in the video description. Thank you for listening. Please like, comment, subscribe, star, and upvote.